So a quick definition, I guess. What is reverse engineering? It's taking apart an object to see how it works in order to duplicate or enhance the object. Why did I start this project? My interest was to dump the cryptographic keys generated by the SMB server used for encryption. Windows doesn't provide them. There is no way to see them. I've bugged a lot of people at doc help for, which is basically Microsoft protocol support to how to do this, and it's unfortunately not possible. So this is something I had in mind for a while. Being able to see the keys would allow for decrypting the traffic in Wireshark, which is very useful, I think. It's also a fun project to learn more about internals of the server and debugging and reverse engineering in general. So yeah, it's useful for if you're working on your own implementation of SMB encryption. It's useful to debug to see if you get the same keys as the server. It's useful for decrypting, as I mentioned. So yeah, this was my project. So the talk will very briefly talk about how the Windows kernel is architectured, some of the differences and similar things with the Linux kernel, which is where I usually work on, what I usually work on. How did I found the code for the SMB server within Windows? How, which modules are being used for the server. I'll talk a bit about WinDBG, which is Microsoft developed official debugger, let's say, and how to debug the Windows kernel. I'll talk about disassemblers and static analysis tools, which I used to understand better the binary modules. In this case, I use IDEA Pro, which I'll talk also about a bit. I'll talk about where the keys are generated and ways you can dump them automatically. I'll give a summary of the solution I've implemented. I have a little demo, which hopefully will work. We'll see about that. And finally, questions and everything. Okay, so before I go further, I should mention that after bugging dochelp for a long time, I finally learned from Obaid. So a lot of thanks to Obaid for providing this information. Turns out this was actually available for a while, since 2015. So the thing is, if you're not interested in the keys themselves, but just the unencrypted traffic, you can actually already dump SMB before it gets encrypted on Windows. So with NetSH, you would do NetSH trace start. You would ask the provider called Microsoft Windows SMB client in the case of the clients, and server in the case of the server. So this will start recording your trace. You can run NetSH trace stop to stop recording. It will produce a ETL file, which cannot be opened directly in Wireshark, but you can convert this ETL file to PCAP, which Wireshark can open via this tool developed by Microsoft on GitHub. I've put a link to Obaid. He also made a presentation about how to do this, which is very well done. I recommend you to watch it if you're interested in that subject. Okay, so an overview of the Windows kernel, I guess. Very briefly, at the bottom you have your hardware. You have the hardware abstraction layer, which is providing abstraction for the rest of the kernel, so that you don't have to directly talk to the hardware. You have the core kernel operating system in white here, which exports a bunch of functions that other modules can use. Those other modules can be file system drivers or other kernel mode drivers. So this is all in kernel space. Once you cross to user space, you have the Windows API, which is sort of a mix of the libc. I mean, it's not really the libc, but it provides function implemented within the library, the API, the library. It's multiple modules. It's not just one binary, but that provides different functions, which themselves can do system calls to the kernel. Usually, applications are not supposed to directly issue the system calls. They go through the Windows API, although it is possible, but yeah, it's not really usually done. You can have user mode drivers, which they use specific system calls that the kernel provides to implement drivers. This is done for security purposes, so that the user mode drivers don't crash your whole machine if they have a bug. So the SMB server is implemented as a kernel module, which is different from Samba, which Samba is in Linux is in user space. There is current work in progress for a SMB server in Linux in kernel space as well, but this is a different topic. So yeah, the SMB server is implemented as a kernel module, which are called drivers in Windows terms. Most drivers are stored in the Windows folder within System32 drivers. They use the .sys extension. They use the PE header file, which file format, I mean, which stands for portable executable. It's the same header which is used for executables and DLLs, shared libraries. So if I quickly summarize, Windows and Linux for those things, you have different locations. So Linux usually stores them in /lib/modules. This is all your kernel modules. They usually end in .ko file extension and use the elf file format, which has sort of the same purpose, but is done differently. So where is actually the server? So my first attempt to find this information, I did a very simple looking for the string related. So the string command, I copied over all the sys files over a Unix system, and I run strings, which basically looks at the file, and anything that looks like an ASCII string, it will that is at least 8 characters long. It will actually just print a list along with the file name it appears in. I just grep for SMB2, and if you run this, you end up having those files listed. The MRX files are SMB redirectors, which is basically the client part of it's the SMB client, the file system, SMB file system. And the SRV modules are the server parts. So there are 3 modules for the server. On this listing, you only see 2 because one of the modules is for SMB1, which is slowly being deprecated by Windows and doesn't actually appear on the system I run this command on. So you have 2 front ends, srv.sys, which you might actually not find on your machine. And you have srv2, which implements the SMB2 and above version of the protocol. Both of those modules end up calling function in another module called srvnet.sys, which has the common code for both module. Although this diagram shows srv.net being bigger, if you look at the size of the binaries, the srv2 is actually bigger in size. So I guess a lot of logic is actually there. Okay, so now let's talk about debuggers. So Microsoft has an official standalone debugger called WinDBG. This thing has existed, I don't know since when, but at least I would say 20 years. It allows for user space debugging, remote debugging. It has a rudimentary GUI with a command line interface, which is similar to GDB in the way that it has a REPL. You type your commands, you get an output. It has a GUI on top, but it's basically the same thing. You can use the pure text version as well, which I haven't tried, but they're accessible as well if you install the WinDBG package. These should be available directly from CMD, the console. The commands for the debugger are incompatible with GDB, unfortunately. So if you know GDB commands, you will have to learn a bit how to use WinDBG. And finally, I should mention that there's a new version of WinDBG called Preview, which has a much more modern GUI wrapper and added scriptability features. I think you can script your debugger with JavaScript, which is an interesting feature. This is what it looks like. So you have a panel here where you type your command in. This is similar to GDB. You have your prompt KD for the kernel debugger. You type your command, you get an output. Then you have panels. So here, the local panel, you would see local stack allocated variables, local variables in your function. The stack panel will list the call stack. So you can see the top one is the function I'm currently in, and as you go down is the function that ended up calling that function. On the left panel, if you have the source code, it can actually display your source code. So it can do source level debugging. But if you don't, it will show the disassembly. You can add and remove panels, reorganize them. It's very nicely done. There's a note panel which is very useful. While you're debugging, you can type notes there. It's like a little notepad integrated. It's useful. So yeah. So yeah, as I mentioned, the commands from DGB are different. I had to learn how to use one from the other. By Googling, I found this actually nicely, as opposed to what the name would suggest. The command list is actually pretty nice. The Aaron cheat sheet has made he has made this table with nice equivalent for each debugger. Very useful. So how do you debug the kernel for Windows? So usually it's I mean, there are different ways to go about it, but the way I picked, which is also documented on the Microsoft website, is to use two machines. So on your host, you will have your debugger running, WinDBG. This debugger is waiting for connections, and then you have a separate machine, the debugged target. I use the VM in my case. The VM is configured for remote debugging. So it actually, the debuggy VM connects to the debugger VM. It's kind of backward if it's a bit unusual. There are instructions you can follow on the Microsoft website, which I've put a link. Note that network debugging for the kernel, only a few network cards are supported. So be very careful which one you put if you use VMs or real hardware. I've tried for a long time to use Kimu and Vertio NICs. So despite having the drivers installed, it would actually silently fail. The debugger would wait for connection. That would never happen. Even by switching the NIC to something well supported like Intel E100, which is a very popular NIC, I still couldn't see any connection happen. And you know, I spent so much time on this getting nowhere that I eventually switched to VirtualBox, which is what I found tutorials online using. So this actually worked. So I kept that. Okay, so on your host machine, you run your debugger. On the debugged machine, you install a specific package of debugging tools, which includes this KDNet executables. You need to set it up. So you run KDNet on your debuggy. You put the IP address of the host machine, which is running your debugger, and the port the machine is listening on. It will print out which interface will be used for remote debugging, and it will print out a key which the host has to know. So you have to tell the host this key so that it's basically authentication mechanism to prevent anyone from debugging your machine. As I mentioned, the remote debugging works by so the host creates a TCP server and the target connects to it, which is a bit backward. It's similar to FTP active mode if you're familiar with this. Yeah, so this command will actually set a special debugging mode that has to be set when you boot the Windows machine. So you can tweak and list and etc. all those putting parameters with BCD edit. It's basically like changing grub entries in Linux. You can change menu entries for booting, and there's a debug flag there. So yeah, you can tweak all those things with BCD edit. So you reboot. In the host machine, you go start debugging. You attach to kernel. You go on the net tab because you want to do network debugging. There's other ways to do it. You can use a FireWire, USB, other things. But yeah, in our case, we use net. You put the TCP port you want to listen on. The key that the debuggy printed, the target IP. I mean, this is not required, but I put it there. You run OK. And yeah, so this is the basic setup. Yeah, basic commands for WinDBG. If the reading the previous list is too long for you, you can run. First thing you need to run at least once is .reload, which will refresh all the loaded symbols in the debugger, because initially all the kernel modules are not loaded. I mean, they're loaded in the debugged machines, but you need to tell the debugger to reload it again. Yeah. LM will list the loaded modules. If you're debugging a process instead of a kernel, this usually lists the DLL your process is using. But in the case of the kernel, it will list the modules. The X command is to examine. You can give wildcards expressions there. So in the Windows world, the exclamation point mark is to separate the module name SRV2 from the symbol name it resides in. So for example, this will list all the symbols containing key in the SRV2 module. Then you have sort of xdump commands. All the xdump commands start with a D for dump, and then there's a suffix corresponding to how you want to display the dump as. So B for bytes, D for double words, which is 2 bytes, Q for quads, which is 4 bytes. So since if you use a little Indian machine, you know, displaying bytes and doubles or quads will sort of rearrange the bytes. So this is why it's useful to have those commands. P is to step over, so it's like next in GDB. T is to step into. So if you have if you're at a function which is calling another function, running T will actually step into that function. P will just wait for the function to return and go to the next instruction. You can set breakpoints with BP. You can break on addresses, symbols, or symbol plus an offset. For example, you can break on a function, like let's say the 10th instruction of the function. It would do BP that function name plus the offset of that 10th instruction. And G is for continuing when you hit a breakpoint. Okay. I'll talk a bit about disassemblers and static analysis. So those tools are to look around the binary files. It allows you to explore the function this binary is importing or exporting. So if you have libraries, you usually export functions for others to consume. If you're a binary, you usually import functions from libraries to use them. So those tools usually they do disassembly. Some of them can decompile, so going back up to even C from compiled code from machine language. They usually have cross references, so you can see where a function is called. You can jump to function definitions. I mean, all in machine language, but still useful. If your module or program is using data, like static data, like strings and such, you can get a list of all those things, where they appear and where they're used, etc. It can be very useful. So the most popular static analysis tools, I've given a list of a couple here. You have IDAPRO, which is the one I used for the project, which is the most well-known and most used one. It has been around forever. Unfortunately, it's closed source, but it runs on many OS and handles all types of architectures and file formats and everything. It used to be very, it is expensive, but they recently changed their licensing options, and you can use free or demo versions nowadays. There's Ghidra, which is a more recent tool developed by the NSA, which something to keep in mind. If the NSA uses it, it's probably not too bad. It's open source as well. It's written in Java and runs on many OSs. There is Radar 2, which is Linux only. It's more in the Unix mindset of multiple tools working closely together to do the job. It's very console oriented. Can be harder to start with, I think. For Windows, you have x64dbg, which is open source, Windows only, has a hello? Is my microphone working?
Yeah, you dropped out for a few seconds, but we can hear you again fine.
Yeah, okay. So x64dbg, which is open source, Windows only, it does decompiling. It looks good. I haven't really explored it a lot, but it looks an interesting option. There's OliDBG, which is very old, but if you look online, you will find many tutorials using it. It's a freeware. It's Windows only. It's a bit dated if you ask me, but yeah, it's available. Okay. Oh, I kept on. I used IDA for this project. So if you open srv2.sys in IDA, this is more or less what you get. On this panel, you see the function list this module contains. So in order to get those symbols, usually you would need debugging symbols, which Microsoft actually provides. So Microsoft has servers which you can query. You give us sort of a checksum of the binary you're looking at. If this binary has ever been released in anywhere public, they will provide symbols for it. So it's a very nice thing from Microsoft. You can exploit, take a use, yeah. So you access all those symbol names. If you double click on one, you will jump to its definition on this main panel. So basic overview here. I'm assuming you can see my mouse, right?
Yes, we can see.
Yeah. Okay. So you have the function name here. Then you have IDA can knows about how parameters are passed to functions. So the ABI it's called. So the ABI for x86 64 on Windows is to pass arguments through first registers and then eventually the stack. So IDA kind of take guesses at what things on the stacks are coming from. So for example, it knows arg. Usually things prefixed by arg means it's a parameter that was passed in. And if it's var, it means it's a stack variable which is only used, which has been allocated for it's a local variable only used for that particular function. You can rename those symbols. So if you figure out what something is used for, you can rename it. It will sort of propagate it in the rest of the code. So here I've figured out the handles of the keys. So I put a key handle and it will be used in the rest of the code. So yeah, very useful. So yeah, what I was looking at is this box here. So the previous box here is this box here in dotted. What IDA shows you is actually a graph. Every time there's a condition or a test and there's two output, either true or false, it will jump to different spots. All those spots are sort of made into boxes in this graph view, and you can pan and move around this view, zoom in, zoom out, move the boxes around to help you understand things. Follow so each arrow will have a color. If it's green, it's true. If it's red, it's a jump which is taken. If it's false, and yeah, it's by moving things around, you can it helps understanding the logic. So IDA also has a decompiler. It's very raw. For example, all the pointer types will show up as 64-bit ints, mostly. If you have, so this is the same function being decompiled. The local variables, so IDA doesn't know about structs. So if you have a consecutive array of memories, it doesn't know about the struct, so it will show up as a list of ints, for example. So it's not necessarily reliable, but it's something that can help. Again, you can rename, if you figure out what a variable is for, you can rename it, and it will the IDA will propagate this name in all the functions. So one thing I didn't mention before is in this listing, IDA was able to figure out that this call instruction I've made was to a function that was imported. So this is an existing external function that the module is calling. So yeah, IDA can resolve those and put the name of the symbol here, which is also helpful. They show up again here. So yeah, very, very useful. By looking at the function names, you can deduct types and sort of the objects the code is dealing with. So for example, here you have all the SMB2, all the functions with reference in the name and dereference in the name. These functions are used to keep track of reference counts for the objects. So for example, SMB2 reference session. If the session is shared between multiple threads, multiple users, each user will increment the reference count, and when the user is done with the object, it will dereference it. So that way, when the last user dereference the object, the reference count will reach 0, and this is when the deallocation actually happens. This is how you usually do memory management in a multi-threaded context. So just by looking at this, you can know what are the objects. Those functions, they usually take a pointer to the object. So you can tell IDA that the argument of this function is this type, and it will propagate this type in the rest of the code. And so iteratively, by doing those annotations, you can deduct and propagate more and more types and get better decompilation output, basically. In those functions, since they basically do +1 or -1 to int variable within structure, you can also figure out which offset the reference count is inside the structure. Similarly, for all the allocation functions, so this one allocate session, all those allocation functions will usually call the equivalent of malloc, something to allocate memory, which are standard functions in APIs. So IDA can tell you the names of the arguments for those functions. In this case, you have a number of bytes. So this will tell you the object allocate session probably returns a session object, and from there you can know it's 230 in hexadecimal bytes long. So for example, you can tell IDA about the structure session, which is this large, and propagate this type in the rest of the code, and yeah, you can get information this way. So these are the techniques you can do to get a better understanding of the code. So by looking at the function names, I found interesting candidates. So one of them is called, in the SRV2 module, one of them is called SRV2 create and register cipher keys. If you put a breakpoint in the kernel and so you connect a client using encryption, and you hit the breakpoint and you step into it. You look at the call it ends up calling, and you can build this nice hierarchy I've made. So it goes, so SRV2, it starts from the session establishment, then registering the cipher keys. At this point, it calls into a different module called the SRVnet, which has this function, which calls in turn this function, which in turn is called the BCrypt generates symmetric key. You have to understand, BCrypt is, as I learned later, is the Windows API for cryptography, which has public, it's a public module basically. So this function does the key derivation generation via BCrypt, and it returns a BCrypt handle containing the keys. As I said, the BCrypt is documented. It's a standard Windows API. So if you look it up, you can find a prototype. And this is the function that gets called. The second parameter is actually, so the second parameter will be filled by the function. It's an output parameter. So this is what we want actually. The only issue is that this BCrypt key handle is an opaque type. It's like a void star pointer. We don't know the size of it. We don't know what it contains. But yeah, it's opaque. But we do know that we're looking for AES 128 key, which means it's 60 bytes long. And we know that the Samba SMB client can already has to generate the same keys when it connects to the server. And there's an option I've added to dump them. So we can already see existing one. So my plan at this point was to, we can put a breakpoint after the function that generates the key is called. We can connect to the server with the SMB client, dump the keys from the client side. And in the debugger, we inspect the memory at the BCrypt key handle pointer and just look around for where those keys, where those bytes that we know about from SMB client appear within the memory in the kernel of at the key handle. So that was the basic plan. If you dump some random address, you don't know you will get different, a big hex dump. You don't know how large the handle will be, so you might be looking at stuff which is not part of it, or what is inside it. The keys inside it, sorry, the data which is inside will either be some plain data, which can be counts or enums or whatever, or it can be addresses, which usually, so for kernel memory, all the addresses will start on x86 64-bit. Addresses are 8 bytes long, and the first bytes will always be FFFFF and some constant value, because kernel memory is always stored on the highest values of the address space. So basically, you dump the handle with whatever looks like plain data and it's not the key you're looking for, is not something you look for. And if you see something that looks like an address because it's started with FFF, you recursively dump this and start over and look for the key from SMB client. So you do this or over and over. It can be very long, but fortunately, it turned out to be very quick. So within the debugger, you use DQ to dump data as 8 bytes ints. It will reverse since it's a little endian. So after doing this thing only twice, so very early on in the dump, you actually find the 16 bytes of the key. So if you have the handle here, you dereference it once. The first thing you get in that thing is an address. So you convert that to uint64. You dereference that again. You end up with an address, which if you add an offset of 92, you find the key. So this is sort of hard to read. So I've made like a C-like structure to help understand this. So if your handle, so the key is basically this struct. The handle will be a pointer to that struct. The first thing this struct contains is a substruct, which has 92 bytes of random data and eventually 16 bytes of your key. And this is stored as a pointer. So yeah, this is basically what I intuited from the key. Once you have this, you have the key from the kernel, which is great. We've sort of achieved what we wanted to do. But pulling out the debugger every time you want to do this is a bit annoying. You have to set up the whole debugger debuggy VM. It's not very practical. So how can we automate this? So the first solution would be to just patch the SRv2 module. So you would open it in some X editor. You will add instructions to dump to the equivalent of a printf to dump your key, and change the code after the key is generated to jump to your code to dump, and then jump back to where you came from. So yeah, dealing with all of this implies that first of all, if you change the binary, the kernel won't load it anymore, because modules are signed. So if you change them, the signature will be different, and the kernel won't load it. It won't accept it. It won't accept it. It's tricky to add additional functions. So I mentioned a printf, but if the module doesn't use printf, you have to add printf into the import module, import table, I mean, so that you can make this external call. And you have, it's a lot of things to deal with. Everything has to be done in assembly, and it's not practical. And every time a new build of SUSE Server 2 comes out, you need to refigure all the offsets again. So it's not really reliable long term either. So solution B, we can write a new driver that once loaded, so we leave SRv2 untouched on the disk, but we have write a new driver that once loaded looks at the loaded version of the module and patch it at this point there. Because once we're in kernel space, we can do whatever we want. We can self-sign our own module. So basically, we will have to add some new certificates to your machine and then be able to load the module. Or otherwise pay for someone to sign it, but that's unlikely to happen. You can use any API because your module is written in C or C++ or whatever. You don't have to deal with import tables. You can just use whatever printf or whatever. But you still need to patch SRv2.sys in memory, so you have the same issues as before in terms of figuring out offsets, and every time the module is updated, you have to figure this again. So not practical. So a third solution I thought about is if you recall the call graph, which is the code path taken to generate the keys, you start in SRv2, but eventually you switch to, you make a call to SRvNet module. So doing external call like this gives you an opportunity to easily hook into that function. So basically, you could write a new driver that hooks into SRv2, not by patching directly the code, but just by intercepting the external call to the SRvNet module. So SRv2 would call, instead of calling directly SRvNet, it would call your code, which your code will call SRvNet. SRvNet will return back to your code. At this point, you can read the keys and return back to SRv2. So it's sort of intercepting the call. So how to do this? I'll do a little refresher on dynamic loading. So PE files, which is the file format of kernel modules, they have export symbols, which are usually used for libs, and import symbols, which is for external calls. The PE header has an import and export table matching those two things. This table is sometimes called the PLT, procedure linkage table. Those table list the symbol name. So the actual symbol name is stored in ASCII for all the exported symbols, which are public in a way. And the address where the function is called. So obviously when the module is on disk, the address is all zeros. And once the linker or the kernel in this case loads your module, it will fix up the location of the, replace the zeros with the actual address of the function you're trying to call, basically. So this is a bit hard to understand, so I've made a lot of diagrams, which probably will clear everything up if it's confusing. Okay, so you have two modules. You have B, which is already loaded at base address. This B doesn't do any external call, so the import table is empty. This B module implements a function called func_in_b, which is at offset 123 of this module. This function simply does return 42, basically. EX is used as the return value register for a function in the x86 ABI. So this basically returns 32. The export table will have func_in_b, which is the symbol exported by this module, and it will have the address where this function lives. So you take the base offset of the module and you add the offset of the function, and you get this final function. Now you're trying to load the module A, a different module. So this is not loaded yet. It's about to be loaded. So this is what it looks like on disk. You have your import table. So this module basically calls func_in_b. But to do this, since when you compile A, you don't know about B or anything, you just have the prototype of B. So you're saying, okay, I need func_in_b, which is at an unknown address at this point. I don't need anything. I'm not exporting anything for anyone else, so I'm not exporting anything. And in the actual code, what I do is I call into this table at the offset func_in_b. So func_in_b offset here, the compiler knows about because it's just the offset of this part of the binary. You're just accessing that element in the table in order to access that address. So you basically, when you do this, you're trying to call those question marks. So this is what is on disk before you load. When you load A now, what happens is the kernel or the linker will load A, will look for imports and look for A is trying to use func_in_b, will look for all the modules already loaded that export func_in_b and just simply overwrite with the actual address used. Yeah, so at this point A is loaded. Oh, sorry. At this point, A is loaded, and yeah, if you call func_in_b from A, it will look here, and eventually reach this point, do this, return here, and everything works. Okay, so how do we hook into this? So let's assume we have a third module called hook. It doesn't import anything. It exports a new function called the hook function b. What this function does is it calls the real one. In this case, it will just increment, so whatever function b does, it will just return 1 plus that, basically. It's a simple wrapper. So it exports this function, yeah, as we know, okay. So the first step that hook needs to do is you need to store the current value of where function b is, the real one. So for this, you have to parse, you look into memory, you look for a.sys in memory, you parse the header there because it's still there when you load it, the header. You look for this entry in the table, look for the current value, and you store it in the variable in hook called real function b. So now we have this address here. So that's the first step. The second step is now that you kept a copy of this function, you overwrite the one in a.sys with your hook. So yeah, so in a way that a will, when it thinks it's calling the real one, it will actually call the hooked one. So now you end up in this situation. You have your 3 modules. Module A is calling, when it's calling function B, it's actually calling the one in hook. Hook is actually, the hook function is actually calling the real one, which is here. So what happens when you run the call? So you access the function B element in your import table, in which here. This in turns, once they reference, it will call this hooked function. This in turn calls the real one, which is here. This returns 42. It returns at this point. We run the increment AEX, and we return back to our initial A. So A thinks it has called B, but actually it has called hook, and the hook has done the work of calling B. So okay, so to do this patching driver thingy, I used Visual Studio. I've just followed, Microsoft documentation for writing device drivers. It's actually very well documented compared to the Linux world. They have a lot of people writing this stuff. Has a lot of diagrams, well organized. A lot of links. Yeah, very well done, I think. Once your module is loaded, the first thing it needs to do is find the SRv2 module base address. Once it has the base address, it will parse the header, PE header, to find the import table and find those this function in the table. Copy the address, which is the real func that needs to be called. Override the entry with our hooked function, as we saw in the diagram. And when you unload your hooked or hook, we just restore whatever addresses were there, so that unloading our module will restore the basic functionality that was there before. And finally, in our out function, the only thing we need to do is call the original one and just simply dump the result that the function made. So in this driver, I just simply write append to a file and see. This is a very bad practice, but I don't really care for this project. I mean, if this was done properly, you would probably do some sort of IOCTL or whatever to access it, but yeah. So I mentioned only one function, but actually this function gets you the keys, but you also need the session ID to be able to really exploit this in Wireshark. So I've hooked another function which gives me the session ID, but it's doing the same thing, so I didn't really bother mentioning it. It's doing the same hooking system. So while doing this, I had many little issues. So for example, there's no API to find the base module address of a loaded module. So I've looked around online, talked with different people. There are undocumented calls you can make to find this. So they exist. They're exported by modules, but they're just not exported in some public header file. So yeah, the idea is to just loop over all the module list and parse the beginning of each one to see if one matches SRv2. Another issue I run into is you cannot write into read-only memory. So all the memory on your system is stored into pages, and each page can have different permission bits. You can have read, write, execute permissions. Fortunately, you can, since you're already in the kernel and you have basically access to everything, you can just change the mapping of that page for the time you need it. So you add the read and write permission while you patch, and you can restore it afterwards. And finally, the final problem was finding the number of and the size of each argument of the function I was hooking. So this is supposed to be documented in the, like, how parameters are passed to functions is standard across all functions. It's documented, so this will tell you a bit more about it, but it's not very obvious sometimes what is actually happening. So yeah, there was some trial and error there. So even though we could,
I'm sorry to interrupt, but just out of respect for the next speakers and so that we can keep the schedule, I have to ask you to wrap up your talk, because the next talk should have started already, but it's fine. We can eat into the break a little bit, but not too much, I'm afraid.
Yeah, okay. I was under the, I thought I had an hour anyway. I'm almost done anyway, so I'll skip on the issues, I guess. And I'll just go to the live demo, which is the final thing. Okay, so hopefully this will work. So I have my Windows 10 VM here, which has a SMB server running. I will connect to it via SMB client, enabling encryption. I need to load my kernel module, which will do the dumping. I register it, I start it. I run SMB client, which is connecting to the server. Okay, I can check the, SMB client knows about the keys, but we can see that here we have a new file that has appeared at the root of the disk, and it has found the session ID here, which matches what you see here. It has the server in and server out, which matches server in and server out here. Yeah. Yeah, that's it. I'll just quickly finish up. I have one more slide. So yeah, the code for the driver is on GitHub. It's only for Windows 10. Thanks for many people who helped me throughout this. There's a Reddit reverse engineering thingy, a lot of code online, and yeah, that's it.